Okay, now we started with problem number 4. On problem number 4, what is the wavelength in meter associated with the radiation of each of the following frequency? Let's do it for one. They're all identical. The only thing is different is the calculation, and I would recommend you to practice, but at least to understand the one of each letter, how to do it. They're all identical. What is the wavelength in meter? They're asking for the wavelength and in meter. In meter, associate with the radiation of each of the following frequency. So they're giving you the frequency, and it's 1.00 by 10 to the 14 seconds to the minus 1. You just have to use the formula frequency multiplied by a wavelength. The speed of light is equal to the frequency multiplied by the wavelength. And they're asking for the wavelength. It would be the speed of light divided by the frequencies given. And the speed of light you're going to use is 3 by 10 to the 8 meter per second. And this is given in second to the minus 1. So it's just plug it in. There's no conversion or anything else. So wavelength would be 3 by 10 to the 8 divided by 1.00 by 10 to the 14. And this is seconds to the minus 1. And this is meters per second, which is going to give you seconds. Seconds cancel out, and wavelength would be given in 3 by 10 by 10 to the 8 minus 14 minus 6 meters. You can also convert it to nanometer by multiplying by 10 to the 9th. Now let's go ahead and do number 5. As I don't have too much space here, right? I have the option of copying and pasting, but let's go ahead and do number 5. Let me do something here. Let me go ahead and copy this on a new page, the second part, so we can solve in one page the first part, and I can just take this out and make a new one. And this is homework 4 part 1, and it would be 11, and it would be the problems from 11 to 16. Okay, 11 to 16. Now let's go back to what we were doing. So, and let's do now here, and this one, number 5. This is basically the same. Now they're asking me for the frequency and the energy per photon. Let's do one so we can make sure we understand how to do it in per photon. Or I give you the formula. Again, you use C. In this one, again, you're going to go ahead at number 5. You use C equal the wavelength multiplied by the frequency, right? And they're asking you the frequency and energy. They're asking you for the frequency, and they're giving you the wavelength. So it's C divided by the wavelength. One important thing is just remember always that if the wavelength is given in centimeter, you always have to convert for meter. If it's given in nanometer, you always have to take it in meter. Why? Unless you convert the speed of light. But generally the speed of light we use, the constant is 3 by 10 to the 8 meter per second. So to avoid any confusion, just take it to meter, and you always work with those units. After you get this, after you divide and you get the frequency, you use energy. I'm not going to solve it, but tell you how to do it. Energy is the Planck. Energy per photon would be this one. Multiply Planck constant multiplied by the frequency. I don't remember exactly. 6.634 by 10 to the minus 34, I think so. I'm not sure about the constant right now, but you can look at it in your book or on the PowerPoints is there. So you plug in the constant and you find the energy, and this the Planck energy multiplied by the frequency you found on the first part of the problem, and then this would be the energy per photon. Always the Planck energy is energy per photon, because the photon is the minimum amount of energy that it's like the package of energy. It's quantified. It's the quantums of energy. Now number 6, and what is the frequency and wavelength in meters of electromagnetic radiation? Well, now they're giving you the photon energy, and then you have to find out. You have to find out the frequency, and you have to find the wavelength. How do you know number 6? If I'm giving energy is equal to h multiplied by the frequency, right? And they're giving you the energy already, that let's say in letter 6a, the energy 4.0809, it says there. 4.09 by 10 to the minus 19 joules. I think it's that value. Let me double check. Yeah, minus 19. Here says Planck constant 6.63 by 10 to the minus 34. So you go ahead and you find first the frequency. You have the Planck constant here. Let me write down this because it's a problem number 6. So that way we can separate it. And then you got here that they're giving you the energy of 4.09 by 10 to the minus 19. And let me write the Planck constant now. I saw it and I remember 6.63 by 10 to the minus 34 joules multiplied by second. Those are the units. So if you plug in the values here, the energy is 4.09 per photon by 10 to the minus 19 joules equals to the Planck constant 6.63 by 10 to the minus 34. Okay, joules multiplied by seconds, and this is joules multiplied by frequency. You just divide by 683 minus 34. It's going to give 4.09 by 10 to the minus 19 divided by 6.63 by 10 to the minus 34 seconds. Okay, that gives me 1 over second, the units. It's the units of frequency. And the frequency for this 6A it is equal to 6 by 6.17 by 10 to the 14. Second to the minus 1. Now you got this, and what you have to do is simple. The only thing you have to do now is find from the equation, speed of light is equal to frequency, wavelength multiplied by frequency. You got the frequency, you got the speed of light, and you have to find out the wavelength. It's equal to the 3 by 10 to the 8, which is the speed of light, meter per second, divided by 6.17 by 10 to the 14, 1 over second, which is the same. So outside inside, second and second, and it gives you a value of 4.86 by 10 to the minus 7 meters. And that's the answer. Now the other one, you can do it exactly the same way. Let's go to number 7. If each atom in 1 mole of atoms emits a photon of wavelength 650 of an 650 nanometers, how much energy is lost? Express if each atom in 1 mole emits a photon of wavelength 650 nanometers, how much energy is lost? So to do this, you have to calculate the energy per photon, right? And then what you have to do is multiply by Avogadro's number, because it's the number of atoms you get, or the number of photons you get in 1 mole of atom. So you got here, right? Let me solve it then better. I'm going to solve number 7. Express the answer in joules per mole and kilocalorie per mole. As a comparison, note the burning of 1 mole of methane produces 891 kilojoules of heat. That would be the heat of burning methane is 891 kilojoules per mole. So let's do number 7 here, okay? And they're giving you that the wavelength, right? They're asking for the energy associated with 1 mole of atoms of a wavelength of 6.50 by 10 to the minus 7 meters. And let's do they're asking you first for the energy lost, because that is the each atom in 1 mole of atom emits a photon of 650 nanometers. That is the wavelength of a photon, and it says each atom in 1 mole of atom, and 1 mole has 6.022 by 10 to the 23rd atoms. 1 mole. So that means that 1 atom emits this wavelength. How much would be the energy loss in 1 mole, in the whole mole? You have to multiply by Avogadro's number. So let's calculate the energy, the Planck energy per photon, by the frequency, but the frequency would be equal. Again, we have to do the same thing, and speed of light by wavelength is equal to the wavelength multiplied by the frequency. So the frequency would be equal to 3 by 10 to the 8 meter per second divided by the wavelength. And the wavelength here is 650 by 10 to the minus 7 meters. Meters, and you get the frequency, which is gonna be you can do it directly too. You can plug in the value of frequency here. So you find out the frequency here, or you can do, because I'm not gonna do it with a calculator, I'm just gonna do it this way. Energy is the Planck constant multiplied by the frequency, but you know that the frequency from this equation is equal to the speed of light divided by the wavelength. So what if you plug in the frequency here in the equation with this value? So it's going to be c over speed of wavelength. So the energy of a photon would be equal to 6.63 by 10 to the minus 34 joules multiplied per second by 3.00 by 10 to the 8 meter per second divided by 650 Okay, remember, that's that. You can do this directly, or you can do it this pathway too. 650 by 10 to the minus 7 meters. And again, meters and meters cancels out. Seconds and second, and it gives you in it gives you in joules. But this joule is per photon or per mole, per atom. Okay, we're talking about the same thing. Photon refers to energy. Atom refers to the particle. The particle and the molecules. Okay, so when you're talking about molecules, so now energy is equal to 3.06 by 10 to the minus 19 joules, and how, per what? Or per photon or per atom? Photon, which is the same as energy is equal to 3.06 by 10 to the minus 19 joules per atom. But how many atoms you have in a mole? Because remember, we have to take it to 1 mole. So we have to multiply this energy by Avogadro's number, right? And we're going to get the energy per mole. Okay, and it's gonna be 3.06 by 10 to the minus 19 joules per atoms multiplied by 6.022 by 10 to the 23rd atoms per mole, right? And so what do we have here? We have that the energy per mole is going to be equal to 1.84 by 10 to the 5th joules per mole. Now it says to express the answer in kilocalories, kilocalories. And it's basically the energy per mole in kilocalorie. Let me write down the conversion. 1 calorie, right, is equal to 4.184 joules. Or, which is the same as, because if we take it 1 calorie, 1 kilocalorie is equal to 1,000 calories. So we do this both conversion. We first take it from joules to calorie and then to kilocalorie. So the energy would be equal to 1.84 by 10 to the 5th joules per mole. Now let's take the joules to calorie and then to mole. Desired unit is up, and then to kilocalorie is 1 calorie on top, given is on bottom 4.184 joules. Joules and joules cancel out, right? And now let's take it to kilocalorie, which desired unit is on top, right? And given in the because it's the one we obtained from the first conversion, so it's calorie and calorie, and it's gonna be kilocalorie. So the final result for this energy per mole is gonna be equal to 44.0 kilocalorie per mole. Now it says to compare it to the one released by 1 mole of methane, right? And it says the comparison, note that the burning of 1 mole of CH4 produces 891 kilojoules of heat. but it's, how can we compare calories to, it's, let's look at this, 184 by 10 to the fifth, if we convert it to joules, hold on, so we compare, that's why I'm doing this, so we can compare it to the methane, and its energy of 1 mole equals 1.84 by 10. If we divide it by 10 to the third to the second, so it's going to be 184 kilojoules per mole. Then I made a conversion to kilojoules, so we can compare it to this one, right? To this one, 891 kilojoules of heat per 1 mole of ethane. It's around the same thing. We're always talking about 184, 600. So it sounds about right. So now let's look number 8. And 8 says calculate and compare the energy of an X-ray photon with that of a microwave photon with wavelength 1.0 nanometer. But what you have to do is calculate the energy for each one from, and I tell you how, from the wavelength with the speed of light formula, you calculate the frequency for both, this one and this one, and then you compare both energy, which one is higher and which one is lower. Now the human eye can detect, let's look at number 9 for a second. The human eye can detect as little as 2.35 by 10 to the 18 joules of green light of wavelength 510 nanometer. They're giving me the energy, okay, minimum energy, and they're giving me the green light of 510 nanometer. Calculate the minimum number of photons of green light that can be detected by the human eye. Well, you know that the energy given here, as little as, this is energy, is the total energy, okay, and this is the wavelength. So why don't we do something? Why don't we calculate the energy of that wavelength, and that would be the energy for photon. We are number 9. Yeah. Number 9. What happened with this? Oh. Okay, and number 9, they're telling you to compare both, and they said that the minimum energy absorbed is going to be 2.35 by 10 to the minus 18 joules. And then what they say that the green light has a wavelength of what? Of 510 nanometers equals 510 nanometer. So what is the first thing? Let's calculate the energy of a photon. If we compare it to the minimum energy that the human eye can detect, we can know the number of photons, because that is the total. For all the number of photons, this is just for one photon, and it would be Planck constant multiplied by the frequency. Or we can just plug in how I did the other problem. We just can plug in H multiplied by C divided by wavelength. Why? Because I'm plugging in the formula here already of the speed of light. So energy of a photon would be equal, right, to the Planck constant 6.63 by 10 to the minus 34 joules multiplied by seconds, right, by 3 multiplied by 3.00 by 10 to the 8 meter per second divided by What is the wavelength? 510 nanometer. Oops, but let's stop, you see. And is that the wavelength, we have to convert it to nanometer. How do we convert the wavelength to nanometer? Let me go ahead and do it here in red so we don't get confused with part of the problem because I don't have space where else to do it. Well, maybe if I try to move that, no. Let's do it in red here down. And after we get it, I put it in a box and we'll take it to that one. So we got here that the wavelength, right? It is 1 meter is equal to 10 to the 9th nanometer. So we got 510 nanometer. So the SI unit would be meter, 1 meter, divided by 10 to the 9th nanometer. Nanometer and nanometer cancel out, and it gives you what? 510 by 10 to the minus 7, because we take it to standard scientific notation, don't forget this, by 10 to the minus 7 meters. So now, how I said, I'll put it in a box, right? And I'll plug it in here. And this comes here. Why? Because I need to cancel out the meter. So let's plug in red 2 by 10 to the minus 7 meter. So meter and meter cancel out. So you're going to get second and second cancel out. You're going to get joules. And it's going to be joules for photon. So the energy, let me keep going back here. The energy of one photon, okay, at that wavelength is going to be equal to 3.90 by 10 to the minus 19 joules per photon. Okay, so now energy per photon. So what is the minimum amount of energy? Energy was that the human eye can detect was 2.35 by 10 to the minus 18 joules. So if we divide this by this energy by this, that is for each photon, it tells us how many photons the human eye can detect it. Because the total energy is always the number of photons, right? Total energy is the number of photons, right? By the energy of each photon per photon, okay? So if you divide the total energy by this energy, the Planck energy per photon, you're going to obtain the number of photons. So in this problem, it gives you, what's the total energy? This 2.35 by 10 to the minus 18. And this would be joules, right? Joules, the unit's joules, divided by 3.90 by 10 to the 19 joules, 19 joules per photon. As you see, photons give us up, and this should give you 6 photons. So the number of photons is going to be equal to 6. And that's the answer for that question. Now number 10, okay, let's do something. Let me cut it out here. It's getting real late, 12:35 a.m. So I'm going to leave it there, and tomorrow I should be able to finish this homework and start with the part 2. Okay, so see you tomorrow.